Thank you, Varsha, for those kind words, and welcome everyone to this ISTVS digital event, where today's speaker is Professor Jim Hambleton from Cambridge University, where Jim has particular interest in soil mechanics and geotechnical engineering. Jim, from rural Wisconsin, completed 3 engineering degrees in neighboring Minnesota before moving to Australia for 6 years to lecture and continue his research interests. When returning to the US Midwest, Chicago Midwestern University near Chicago, one of Jim's research projects that ISTVS colleagues are very interested in was a National Science Foundation Terramechanics related research program, which Jim is going to explain in his talk and outline some of the key outcomes. Jim took up his current post at Gonville and Caius College, University of Cambridge 2 years ago, but still maintains strong links with his former institutions. I'm very much looking forward to this talk, and I'm sure as the rest of the audience are. And today's talk is going to be titled Odyssey from Geomechanics to Terra-Robotics and from Rural Wisconsin to Cambridge. So thank you, Jim, for agreeing to talk to us, and we're very much looking forward to hearing your presentation.
Thank you very much, Alex. That was a wonderful introduction, and I'm glad you framed it this way. Thank you to Varsha for doing all of the behind-the-scenes work, and today even some of the in front of all of us work. And thanks very much to ISTVS for being the host for all of this. As Alex said, he actually got in touch and mentioned explicitly this National Science Foundation project, this career project, and therefore that's the way that this talk is framed, is around that, including a lot of the lead up to it, which I hope is of some interest. So I'm imagining I will get into some technical matters, and I hope that's okay with people listening. I will get into other matters about life and my trajectory and how this all came to pass, including the front end of it. And this will surprise Alex, but I actually this is an important part of the story. So I have some slides on my journey. I was indeed born and raised in Wisconsin. We have a tendency in the US to look west, to yearn to go west. And you don't have to look very far to the west of Wisconsin to find a big land-grant university that does lots of interesting research. I was thinking I was going to do structural engineering, which I will come back to. And it was in my last year at Minnesota that I met this gentleman, a wonderful human being with deep technical knowledge, who got me very interested in things beyond structures, solids and soil mechanics and geomechanics in particular. When I finished there, I needed gainful employment, and Andrew Drescher was very encouraging to say, look at academic positions, look all around the world. And my wife was very instrumental in saying that of all of the places that you're looking at, this one that's in Australia, University of Newcastle, not England, but Australia is the most intriguing one. And at the time, Professor Scott Sloan was the director of the center that had just been established, this Center of Excellence, which involved multiple universities within Australia and multiple industry partners. And it was just a fabulous time to be there. And I actually have lifelong collaborators, one in particular who is here at Cambridge that I met in Australia, and those became lifelong links. So here we are in Newcastle. There's the attraction that I mentioned, and it's obviously an imperative to learn how to surf if you have the opportunity. That is me on the left. After I more or less learned to surf. As Alex mentioned, the US came calling in figuratively and literally to come back, and that was a difficult decision, but we are Midwesterners, so Northwestern University seemed like a very natural place to go back to. That's in Northern Illinois, just north of Chicago. And I thought that that was the end of my international travels, and I'm speaking to you now from the University of Cambridge, which is a story of its own that I don't really have time to go into, and I would love to share with anybody who's interested. Before I get into terramechanics and terra-robotics, I do want to have this disclaimer that this isn't the only thing that I work on. And that's, I think, one of the messages that I want to give to young researchers is follow your passions, look all around, but do have something that you focus on. So I am very focused on terramechanics, as is shown here. A part of that theoretically is an interesting subset of problems, evolutionary plasticity problems, which you'll see today, so I won't spend too much time talking about that. And then I did get interested in a variety of other problems, constitutive modeling of soils. I won't spend any time talking about these. When I went to Australia, there was an interesting yield surface and plasticity theory that we needed to show whether it was convex or non-convex, and it turns out that's just an applied mathematics problem, basically, which we had a lot of fun with, and I helped with when they were sort of stuck when I arrived in Australia. I've done work on screw anchors, which are a very interesting geotechnical problem and actually very close to terramechanics because it involves twisting the ground anchor into the soil. It involves moving parts interacting with soil, which you'll see later in the definition I'm suggesting is a terramechanics problem. And then this is a little more exotic. Again, in Australia, I met researchers working on this rockfall protection problem. By the way, what I just skipped over was a real screw anchor being installed. So it's not just theory, but it's also the practice and the applications here. I met researchers working on rockfall protection. It's a large deformation plasticity problem. You have failure of this rockfall barrier, and we got immersed in this and doing this sort of thing. So I don't want to suggest with this talk that terramechanics is my only interest. It's very much front and center as my primary interest. As I said, I want to navigate through how I got here, and I want to appeal to talent wherever we can find it, that there are very interesting problems. I am unusual nowadays, at least among young people nowadays, that I'm naturally drawn to civil engineering. I mentioned this, that I imagine doing structural engineering at some point in my life, and the appeal is right there for all of us. You know, the pyramids are on this chart moving up to the Burj Khalifa, which is just a fascinating engineering problem. I would also say it's not just the structure, but it's the earth beneath. It's the geotechnical problem, which you don't see. And indeed, that was part of meeting Andrew Drescher and getting interested in solids and soils, these things other than slender structural members that really drew me into soil mechanics and geomechanics. Now, very quickly, I want to say structural engineering has its obvious applications, and plasticity and failure are right in front of you. If the structure fails, there's no question that it fails. The two examples I'm giving here are the I-35W Mississippi River Bridge collapse, which is something that we talk about here at Cambridge to our first-year engineering students, oddly enough, this very problem. There's a very well-known case study in structural engineering, this Hyatt Regency Kansas City collapse, which is studied not only. It's a relatively simple engineering issue that's involved, and it's almost more of an ethics issue about there wasn't enough involvement from the engineer in signing off and making sure that everything was going to work in this problem. So that was more or less, you know, I was thinking about plasticity, and I was thinking about it for structures, and nowadays I've come to appreciate all of the plasticity problems that are all around us, including in soil mechanics. And the easiest way you can see that is to walk across the beach. Every time you leave a footprint, that is plasticity. You've left a permanent imprint. There's permanent deformation. And one thing that I can introduce very quickly and incompletely is the idea that if you put more and more weight on your foot on the beach, you'll feel this response. You're going to settle in more and more. There's an initial regime where if you put more and more weight on, you're going to settle in more and more gradually. But you can imagine putting a level of weight on your foot that exceeds this first peak that is being illustrated here, which may or may not be present. And you can see that there's an interesting situation that if you try to put that much weight on there, you're going to sink in until you finally reach the settlement that this curve joins up again. So you're going to sink in immediately, catastrophically. And that's what plasticity theory essentially is all about. There's a wonderful book here. Patrick Salvadorai is no longer with us, but I decided to put his book front and center for various reasons. There's a whole theory of plasticity that you can get into typically in your graduate studies if you're at US University, although here at Cambridge we do teach our undergraduates quite a bit of plasticity. And here on the front cover is a very, very well-known solution about evaluating the bearing capacity, theoretically the limit load that you can put on the surface when this collapse happens. All right, but enough. That was general background, and then I have to tell you more about how I got engrossed more and more in geomechanics and terramechanics in particular. And I've written here my first love, not romantically, but in research, through Andrew Drescher, the advisor that I showed, my advisor. He drew me in through this master's project, which is actually down in the lower right over here. The Minnesota Department of Transportation had this old and seen as perhaps substandard test where they would roll a heavy cart across a newly constructed embankment. This is going to get paved eventually, this surface. And they would use this test roller, roll it across the surface, and they would use the depth of penetration, which is shown here. We measured these in situ and in the field. And they would use that measurement of penetration depth as an indication of whether the embankment was sufficient or not. And if the penetration depth was too large, the contractor would have to go in and compact the soil, do some remediation until it was up to scratch. And now the background of this project is that the Minnesota Department of Transportation was actually not a huge fan of this test. In many respects, they would have appreciated if it was gone, if we could let it go. Andrew and I took the view that this is actually a fascinating theoretical problem. You have, what is the theoretical relationship between penetration depth and the strength of the soil of the stratum? And that was then how I engrossed in soil-wheel interaction, which as I was going through my PhD work, I realized is, of course, not just this problem for the Department of Transportation, but it's mobility. And we're here with the International Society for Terrain Vehicle Systems, so these are no surprises, these sorts of problems. And then other interesting things like land damage. I started to see soil-wheel interaction all over the place. After my master's project and wrapping up this project with the Department of Transportation, I completed my PhD thinking about this on multiple levels, doing numerical simulations. These are large deformation, finite element simulations in 3D, doing experiments, and then doing what I think is my favorite piece of all, the analytical work, meaning can you build mathematically a solution that gives a very, very quick answer to some of these problems, which is a theme that you're going to see recurring throughout this. And just to give you a flavor of what that is, this is far and away the most mathematical set of slides that I have in here, and I don't have any intention of walking through the mathematics, and we don't really need it. You'll see that you can understand the problem without any of the equations or variables that I'm showing. Here's to just take indentation. So we're talking about broadly about any kind of problem where you have an object interacting with soil. It could be a wheel, and that's a nice segue from what we just showed. It could be a cylinder. So here's in gray is a wheel-like object, a cylinder-like object. It's been pushed into some penetration depth, and as it's being pushed in, it's displacing some amount of soil next to it. And that is what I mean by evolutionary. There is a process here. It's not a single state. It's a sequence of states. It's an evolutionary problem. As you push it in deeper, we go to the blue curve, and the force is going to get probably larger, although we saw earlier that it may not if it's a softening response of the material. And the lip of material off to the right here is grown. And I'm actually highlighting two variables in red that are worth noting for this. Kappa is what we're calling the distance by some measure that the lip of material to the right has moved in one increment, small increment of deformation. And lambda is a parameter that characterizes how the distance over which it's being displaced. And it turns out you can walk through, zoom in on this area. You can do some kinematics, as we call it, which is essentially just the geometry relating these variables to each other, thinking about differential movements here. And as I say, I'm going very quickly through this. You ultimately wind up with a differential equation that tells you how this surface is moving as a function of how you're penetrating in. The breakthrough, if you like, I mean, that's a strong word, but the really interesting thing about this whole approach is how do you ascertain lambda and kappa, these parameters? And we said back to the problem that I showed of the foot on the beach in plasticity theory, is it turns out you can actually evaluate that lambda and that kappa from the theory that we already have for foundations, essentially, this bearing capacity problem. We know how to evaluate, if it's not a wheel, but it's a strip footing sitting on a surface, we know how to evaluate the average stress, Q, over the area of the footing, and we can even include lambda and kappa if it's an inclined surface like this in the solution. So the neat trick that you use here is you just plug in the lambda, the kappa, the q that you get from standard plasticity theory when you go deep into the subject. There's a little bit of mathematical work to do that sometimes yields closed form solutions for certain geometries, and you can get analytical solutions to these problems. And you'll see some of these later on. Meaning I have an equation that I can now write down, simple equation, relatively simple, that I can relate. What is the force for a given penetration? I can solve that very, very quickly. Okay, so enough about, and fewer equations from this point on. The point was not to bombard you with equations, but show that there's some rich mathematical analysis behind this, and evolutionary plasticity problems are very interesting. So in comes the autobiographical part, and what Alex had mentioned, and what I intend to talk about is at this stage in my life, I'd done my PhD. I was casting about. I showed you some of those problems that I got interested in, having lots of fun. But I realized if I'm going to keep going as an academic, the reality is that I need to fuel this interest somehow. And there's an expectation, that doesn't happen too long into becoming an academic, that you should probably get some projects set up, apply for a grant, start to pay for some PhD students, master's students to come, pay for some experimental equipment, and so on. And I was thinking about, well, who am I at this point? And I was thinking this evolutionary plasticity problem is very, very interesting. What I'm showing here, and this is really just out of interest, this is in my bedroom in Australia, our bedroom. My wife was very tolerant of dragging in Stockton Beach sand and setting up this bin. If my father happens to be watching, this is the copy of the intellectual devotional that he gave me, which I have read, but turned out to be, if I may, far more useful as a piece of experimental apparatus. This book I was dragging across the surface, taking images, so there's some velocity v, and I was watching how the region of material in front of the book evolves as an evolutionary plasticity problem as you push the book further and further through the soil. So we'll call this the lip of material, the accreted material. We could call it many things. And what I was looking for specifically was, what is the mode of deformation? Is it deforming all within this region? Is it deforming in concentrated zones? I was interested in whether this surface here was avalanching, collapsing. That's a classical slope stability problem in geotechnics. Is the material rolling downhill, or is it deforming some other way? I mean, how is it moving? And it turns out you learn lots of things immediately by just playing around in your bedroom this way. There's another way that you can do this, which is to just tackle it analytically. And I won't go into the details, but here's a little cartoon and a model where you can say, I'll build a model predicting the force and assuming that all of the deformation is concentrated along one well-defined slip surface or shear band, shown in red here. And what I want to do actually is show you what happens if you extend that idea. And I won't go through the mathematical details or anything. I just want to show you the end result, which is the most interesting to look at. And there's some assumptions that we need to make around the way along the way to getting there. The key one being, in the first instance, is it a material that has changing material properties, or are they constant? So the first result I'm going to show you here is without softening. This means if you're thinking about sand, it has to be moderately dense, close to the critical state, so that upon shearing, it doesn't densify or loosen too much. And then that would be, if it were achievable, and in reality it isn't, that would be something where you expect to have the same strength throughout the soil as you're shearing it more and more. But of course, those who know a lot about this know that the properties are immediately going to begin changing once you start to shear. But suppose that it doesn't soften or weaken or harden. It doesn't densify. It doesn't loosen as you're shearing it. It's just a constant strength, constant density. And what you'll see here is the deformed shape. So here's the wall. It was moving from left to right before. Now it's moving from right to left. Forgive me. There's a surface here shown with a bunch of nodes, which are key to the solution to this problem. There's some layers to show you what happens as we change as we move the wall from left to right. And here in red is the band, the theoretical prediction of the band, which at this increment in deformation is happily sitting at the toe of the slope. And this is something that we optimize. The part of the solution of this is that the band position is variable. It can move wherever it wants. And you can see that, in fact, its position is determined by where the load is going to be the least. So what's shown here is if I moved, theoretically, the band to the left, the force required to displace the wall would go up. And if I moved it to the right, again, it would go up, and it would go up very steeply. So there's some optimal here. There's a minimum, a sweet spot, where the force is the least, and that determines the position of the band. And the last thing you need to know here is this alpha is the inclination angle of the slope. So if this gets to be too large, because it's dry sand, it will start to avalanche down the face of the accreted material. So let's see what happens if we start incrementing this in a material that has constant strength. And you can see that the band just moves, translates through the material, moving along, nothing particularly interesting. So the band is advecting, moving through the material, and the inclination angle ahead of the, on this slope here is always less than 20 degrees. And the friction angle that's in here is going to be something like 30, 35 degrees, maybe 40 degrees. So this is well away from failing, because the simplest slope stability model says that when the inclination angle reaches the friction angle, then you expect to see a slope failure. All right, so no softening, nothing terribly interesting, although it is, I would argue. Now let's see what happens if we take this to a dense sand. So if it's a dense sand, if you start to shear the material, it has to start to weaken. It loses its density, it loosens, and it gets weaker. So, and that's a softening response. So what happens when we have a softening response? Same story now, and you can see that I'm evolving this problem, and suddenly the band jumped. And as I keep incrementing the deformation, the band is now going to sit in its current location relative to the wall, I suppose you could say, until finally it jumps again. And if you look down at the optimal load, you can see, aha, there are these little valleys that correspond to the fact that it's been softened in that spot. It's easier to shear it at that spot than others, which explains why it tends to remain in one location before then jumping to the next optimum. Another interesting feature that you see down here is that now the inclination of the slope locally does get to the angle of repose. So when we've introduced softening, we see that there is this avalanche happening as the process is unfolding, which is, as if you study this and look back at the heuristics that I was able to look at from the experiments, that's very consistent with what you observe for a dense sand. So interesting problems. This one arguably much more interesting. You have a periodic progression of the shear bands. They change in locations, they jump around. And here then is, after getting through all the preliminary work, is the sort of summative experiment where we were at University of Western Australia. I mentioned my collaborator, Sam Stanier. We had a student, Alahe, who was working on this, and we were able to do take digital images, do digital image correlation. What you're seeing here are contours of shear strain, and you can see very clearly these bands as they jump from one location to the other. And you can sort of see that actually there is indeed avalanching that's happening over here. You can measure the force as a function of displacement, and then you get pleasing qualitative agreement, in some cases quantitative agreement, with the force that's on the wall, which then jumps whenever the band jumps. So it's not an increasing function. It's a jumpy periodic sort of behavior that we're seeing here. All right, so there's some results that are well before the project that we've been talking about with Alex, but set me on this pathway to thinking about evolutionary problems in general, not just soils and wheels, but cutting problems. And my mind was starting to open to all of the instances where this happens. So in come some things that are more familiar to this audience. I'm imagining the ISTVS crowd here, in fact, is Godwin and O'Doherty, Journal of Terramechanics, which is the journal for the International Society for Terrain Vehicle Systems. There's other problems in geology and at smaller scale. This is a pipeline plowing problem. The point being that when I started to think about plowing and cutting, trying to make a distinction between different modes of deformation that can happen, that's a very rich landscape of problems in itself. And in comes, one of the key pieces of advice that I have in this is I was thinking I'm interested in these problems, but at this stage in my life, maybe I'm a crackpot researcher. I don't know who I am exactly, but I'm doing these experiments in my bedroom. And then, we did the proper experiments. And am I crazy? Is the world going to care about these problems? Is this interesting? And I thought, which is, I think, a natural progression for a lot of people, that I need to start chasing some numbers that would motivate that this really is a grand problem. And it took me a long time to hit on the right keywords to motivate it from one angle, which was I was thinking about how much Earth humans move. And I thought it must be a lot. You put together all of the different Earth moving processes, and it's got to be a lot of Earth that we move. And sure enough, if you're patient enough with it and you work very, very hard, which I did have to work very hard to find this, I found this paper by a geomorphologist who writes very convincingly that we are the most important geomorphic agent. He was interested in natural processes, erosion, transport of materials, and he was also interested in how much are humans doing compared to natural geomorphic processes. And the answer is we're doing a lot. It's enormous. I took the information that I could find in his paper. He estimated for housing, mineral production, and road building alone, he estimated very convincingly that it's 32.5 gigatons per year. I went and looked for the population in 1994 when this was written and divided through to come up that each of us in 1994, apparently for housing, mineral production, and road building, moved 3 cubic meters of Earth each without lifting a finger, just by virtue of living in your house, buying the products that you buy, using roads, etc. And I show this number and it's published information, and I always get a variety of reactions. Some reactions are this number is probably way too small, and certainly 1994 was a long time ago. We've probably only grown in our the amount that we've moved. Very important problem then. At least I convinced myself of that. At the risk of becoming delusional, I suppose, but I thought this is a big problem, very interesting. We have some compelling arguments to make for doing it. I was thinking about offshore problems and plowing and cutting for pipelines, mobility problems across scales. And in Australia, actually, it was that I first started to write proposals, and I was successful with this DECRA, so-called DECRA, which is the equivalent of a National Science Foundation Career Award in Australia, and was working with Caterpillar at that point for a while as an industry collaborator, thinking about how do you model these problems and build efficiencies in how we design earth-moving equipment like the one that you see in the center of this image, or the ant-like problem of many of these machines working together collaboratively to do earth moving across scales. Okay. What happened at this stage, and that's its own story that I don't have time to go into, is I was drawn back to the US. My wife was instrumental in that decision again, although this time she was far less convinced, but we had long conversations about what would be the right move for us and our family. I had children at that point. And at any rate, the decision was made, for better or worse, to come back to the US, to come to Northwestern. And at that stage, I was very convinced that I wanted to spend a healthy amount of my time looking at these, what I was calling then soil-machine interaction problems. And I think that's still completely a valid term. I've been wrestling with the terminology for a while, and I'm open to any suggestions from anybody here about terminology. The idea was we can go further with what we've already done by thinking about using a 6-axis robot as a flexible actuator that can do all kinds of motions. And so here's the lab that Northwestern University was very gracious in giving me when I came there, and they gave startup funding, so it was not a big deal to purchase the 6-axis robot. There's some faces here which are worth pointing out. Jafei Jin is still in the US, and she graduated with a PhD and did a lot of the work that you're going to see here. Jinhao Shi, he's now at Tongji University, happy over there. He's was a postdoc who did a lot of fine work. You'll see his name. Ting Lu is in Australia, and he worked with me at Northwestern and then went to Australia to do a PhD. Nima was a postdoc at the time. He's still in the US, and Dave Ventry was our lab technician. So lots of people helping out with this, and 2 people in particular that you'll see their names pop up again. All right, so we had the robot. We needed a bed. we needed a test bed. And one of the key pieces of advice that I got from the well-established program director at the National Science Foundation, who was there for many years, who was interested in soils and geotechnics, Rick Frigese, is he said, well, before you apply for a bigger grant like the National Science Foundation CAREER Award, which is a 5-year project, it's just, there's more of it. He suggested you should go for something smaller and do some preliminary work, get some data. And one of the things, thanks to interacting with Dan Goldman, I'd seen, and Paul Umbenhauer, who had worked with Dan Goldman at Northwestern University, we were aware of the possibility that you could use fluidization to be able to rapidly reconstitute soils. So in terms of what you start running your experiments on, the fluidized bed makes it very easy to reconstitute samples quickly, flatten the surface, and reach controlled density. So here's Jifei Jin, Jinhao Shi, and me thinking about this whole setup. And I believe in a second here, you'll get to see fluidization happening. Experiments. You want to see some fluidization? This is going to be a real-time experiment. Think building. That is a building there. This is like maybe a gas tank, right? Switch it on, okay? So this now has turned into a boat. Yeah. And our underground structure here turned into a flipped over, so it didn't actually float to the surface, but it was empty. And check that out. Our sand has gone from solid to liquid.
Oh my God.
And Tierney, you heard Tierney's voice. She was worked in the front office at Civil Engineering and very gifted with videos and music, as you can see. So what makes that that video is the music. All right, but as a scientific instrument, the idea here is that you can fluidize the sand and you can reach a desired density. And I've already made a bit of a fuss about loose sand from dense sand. And so it's very important to control the relative density of the sand, which is on one axis of this plot. And it turns out in this bed, you fluidize the sand, and then as you defluidize slowly, you get more and more dense sand. And if you do defluidization only, DO, the green line here, it takes a long time to get to a dense sand just by turning down the flow of air. Oh, by the way, I should have mentioned, I mean, the idea is you're pumping air through the bottom through a perforated sheet, and then you're controlling the flow of air with the pump, with the blower that you saw on the previous slide. So in this case, we're turning down the air very slowly. We get denser and denser, but it's taking a long time to reach a dense sample. And what Jifei had played around with is if you vibrate the sample as you're defluidizing, or after you're defluidizing, you can get to higher densities quicker. And actually this one, defluidizing while you're vibrating the sample, is the one that gives you the fastest pathway to the fastest pathway to a dense sample. But you can achieve the whole range is one of the takeaways from this. You can get to a high density and you can achieve a low density if you just fluidize and switch the air supply off quickly. So that's the test bed itself, and then the 6-axis robot is essentially, in this case, the way we started in all of this is a very flexible actuator which can do all kinds of motions, not just cutting, which is what you're seeing now, but then it could do whatever you want, and it's about to twist, and you could imagine even screwing something in, more complex problems, and a wide range of possible kinematics, possible trajectories that you would follow. So this was the moment. We built the bed. We'd got some interesting results on this. We were moving along, and it felt like the right time to really declare, and that's what you do for one of these career projects. Is it's an unusual grant proposal in a way, because you're kind of making it about yourself. Lots of grant proposals, you have a compelling problem, you argue for it to be done, but you have a team of people and resources are going to be distributed. The spirit of the Career Award and this DECRA in Australia is that it's something to help early career researchers, and you really want to think about who you are and what you want to do or what sorts of problems you want to work on. It's meant to launch you into your research career. And you can see at this stage, I was just enthralled with all of these problems. We're adding now one more issue here, which is bio-inspired problems. There's all kinds of creatures that essentially are involved in moving and manipulating Earth, and those are interesting problems as well. So I crafted this project, and it was that takes a lot of effort. It's sweaty work to think about, what is it you're doing, why you're doing it, motivating it, thinking about a coherent program that you're going to run. And this was the end result, imagining that the only viable way to even make progress with these problems is to have this circular design feedback idea where you run experiments, you try to build analytical models to the extent that you can of the type that you saw. You also acknowledge that that's not always going to work, and in many cases you're going to have to resort to, but many people might be offended by that idea, to numerical simulations, which are predictive, but can work in very general problems. And then, of course, you're going to find out that you're wrong. So there's an interaction between these three, and you keep working until you find something that works. And the ring around the outside is to say that this is not in a vacuum. The idea is these are about scholarship as well as teaching, education. And I'd imagined that I had young children of my own, that we could do lots of tinkering. We could think of model problems that we can study. We could run a graduate course on Terramechanics, which there's another talk on, I'll mention in a second. And then at the freshman level, we could have mechanics students, mechanics being statics, dynamics, deformable body mechanics. That's how materials move, and under loading, the relationship between force and displacement, stress and strain. And I'll show you in a second where you can find more about those two. The tinkering programs, this was COVID era. They were a bit derailed. We'd imagined doing something with the Chicago Children's Museum. We did do some things with the Chicago Children's Museum. We imagined going to maker fairs and having youngsters digging around in soils, because who doesn't like that? And some of that came to fruition, but a lot of it was actually derailed by the COVID pandemic. So I don't have much more time-wise that I can say about education and outreach, and I don't need to, because you're welcome to go, if you're interested in this, to Figshare, or this is also on YouTube as it happens. And I recorded a talk on inspiring interest in geotechnics. I could say terramechanics, and that's, I guess, the point of today. I was imagining advocating for geotechnics. Then today I'm advocating for terramechanics. And I chose this particular shot, which is early in the video, because the notion here is that 500 engineering students, roughly speaking, coming into Northwestern. There's 100 in each section of this general required class on statics and dynamics. And all of the yellow dots are people that aren't interested in anything related to civil or environmental engineering. The red and the green are the people that are civil and environmental. And how many people are interested in geotechnics organically among those? 0 is usually the number. So the 3 people who are in civil, they tend to be interested in structures, and usually, and perhaps other problems. It's pretty rare that they're interested in geotechnics. This is the same problem we have in terramechanics then, is that there isn't a clear entryway into terramechanics from the very beginning, unless you happen to have done a lot in your own backyard in a community. And Alex and I actually had a lot of conversation about this just yesterday, that both of us come from rural areas and would have been very familiar with terramechanics problem at an early age. So at this stage, I'm going to skip over education and outreach, and I'm just going to give you a whirlwind tour of some of the results from the National Science Foundation project, CAREER project. And there are too many to talk about. I mean, thankfully, that's a good problem to have. There are also some of it, we're still working on getting the results out, bringing it together and bringing it to light. But a few key things that at least hang very nicely with what I showed is, I showed you an indenting cylinder, and I showed you a cutting problem. In general, you could have whatever object that's undergoing, moving through the soil and inducing large permanent deformations. And one of the things that Jin Hao and I worked very hard on as part of this project was to generalize this technique that I showed earlier, and we're calling it now sequential kinematic method, which can very efficiently solve these sorts of problems. You saw some examples. There's more examples in the paper, and this one is, I think, particularly impressive. It's a cylinder where you push it way into the soil, deep penetration of a cylinder. In offshore geotechnics, this would be a T-bar problem. You can see, that's a challenging problem to simulate, and you can solve this problem relatively quickly by subdividing the domain into these triangular blocks and doing essentially a glorified version of what I showed earlier, where you're tracking how they move, optimizing in each load increment, and calculating the deformed shape, and then incrementing the solution. And if you plot normalized force versus depth, and you compare, there's an analytical solution out at this point. There is no analytical solution all the way through. There's the shallow penetration problem that I showed earlier. The only complete solution would be to run the red line. You run a finite element calculation, and the blue dots are pleasingly close to the red line, which suggests that you can, in fact, calculate this solution quite efficiently, much more efficiently than using a finite element solver with all of the bells and whistles. Part of this was to think not just about 2D problems like I've been showing the whole time, but 3-dimensional problems. You saw in some of those images, you have deformation to the sides of the object. Some very elegant solutions on steady flow problems by Azarkan and Devenpeck, which inspired some of the thinking about this. And one thing that you can do is start extending this paradigm that I've showed to not triangles, but tetrahedra. So you saw triangles moving within the soil domain, and in that cutting problem, for the 3-dimensional problem, you now have the equivalent would be these tetrahedra. And sure enough, it requires some fortitude with the mathematics, but you can implement everything that worked in 2D and 3D, and you can build very efficient formulations for 3D problems that way. Again, Jin Hao is the champion of this work who made some things happen in 3D. One thing that I'm really excited about, which we've been working on more and more, this has been bubbling away behind the scenes, and we're putting more and more effort into this, is whether or not you can have a semi-analytical model that you have an object moving through soil at some trajectory. It's got generalized forces, HV, 2 forces, and a couple and a moment, and those are going to evolve as you're pushing this thing through the soil. You could imagine modeling that, and this has strong grounding in work done on plate anchors and keying problems in offshore geotechnics. There's some great papers written on this that leap to mind that I can send to people. Mark Cassidy, who's at University of Melbourne, has done a lot of, his name leaps to my mind, and he's done a lot of work in this area. And essentially what you can do with these sorts of problems is model, for those familiar with plasticity theory, you have a generalized yield surface that operates with respect to generalized forces and moment, generalized forces including the moment, including the couple. And you could imagine for this problem a generalized surface that now evolves and changes as the geometry of the problem is changing, and perhaps the strength of the material is changing as well. And then you could calculate using plasticity theory, flow theory of plasticity, the evolution of the forces as you follow one trajectory or another through the soil, which is being illustrated here. Okay, so again, mathematically quite complicated. I hope I sketched the idea, and we've been working on that. And in fact, the first person to really start working on that is Jaffe, who I mentioned and showed. And she was in sand pushing in a plate. So this is, again, the plate problem. You saw the plate in the video. You push it in, but you change the way that you push it in. So push it in, and then a steep inclination from the horizontal, or shallow inclination from the vertical. Then you start to change that inclination angle, so moving more from a penetration kind of a process to a translation kind of a process. And lo and behold, we can measure with the 6-axis load cell that's on the end of the robot, we can measure the forces. We're plotting H and V as a function of displacement, and the blue curves are her numerical predictions based on this semi-analytical model, so far as she was able to develop it for sand. And if you want to know more about that, the only place that exists at the moment, like so many other things, is in Jaffe's PhD thesis, which she graduated way back after the pandemic, and that was a difficult time for all of us in 2021, and then went to work for Meta, where she still is in California. Big loss for the geomechanics community, but amazing that those skills are so portable. And I hope if Jaffe ever comes to see this, will it be inspiring her back to come think about terramechanics problems. She is needed. Okay, the last little piece. I'm very nearly done with my tale, and I hope that this is the right balance of technical material and the story of the NSF project. And this is an interesting dimension of the NSF project that is interesting because Qing Hao, who's now working for ANSYS, he was interested in coding, interested in machine learning methods, and came. I'm very grateful he came to work with me on this project. He was part of the National Science Foundation Career Project that we've been talking about here. And the story here is that I'm going to advocate for is you have to be yourself. I had to be myself when I was imagining what this project would look like. Whenever a new student comes along, I worked very hard to allow them to be themselves. And Qing Hao was really, really interested in using some of the new machine learning things that were coming online, data-driven methods. And I said, why not? Let's give it a shot. I can imagine how this could work. And I'm going to spend a few slides talking about his work on data-driven methods. So what's being shown here are force displacement responses for an indentation problem involving a wedge and a cylinder. And the RITS, R-A-T-T-S, is essentially a finite element calculation, numerical simulation in orange. And in blue is the analytical solution, which you see my name and Andrew Drescher's name here. This is the one that I was alluding to. There's very good agreement between these two. So we have some way of having predictive models that give you the response for these problems. And Qing Hao and I said, well, what if, you notice nowadays there is a lot of effort running these kinds of calculations for essentially the same kinds of problems over and over again. And people are generating, either deliberately or out of necessity, they have projects. They're not necessarily storing this data, but there's a wealth of data that comes out of all of these simulations. And we were wondering, could you build a model, a surrogate model or data-driven model that really didn't think about physics, didn't drive on physics. It was just predicated on the data that you can get from these simulations. And you'll see, I'll show you a bit about wedge indentation, cylinder indentation, and the cutting problem will resurface itself here. And there's some machine learning in here, which I don't think is necessarily the interesting part because you see machine learning everywhere. But what we were working very hard on is to try to think about how you build the architecture that enables machine learning in a useful way and doesn't make it a complete black box. And the interesting part of these problems is this evolving geometry. So what we focused very heavily on was how do you represent the surface as the surface is evolving and changing? You could make an ad hoc assumption about what it looks like. You could say it's piecewise linear, for example, some curved shape is a collection of straight lines. Or this was, again, the breakthrough, although that's a strong word. This was the step that I think is really interesting in this work, is to say, well, why don't we use proper orthogonal decomposition? This was Qing Hao's idea. I don't think this was my idea. Why don't we use data analysis techniques to calculate what the surface is as it evolves? And this is well known across multiple fields, as you saw there. So I'm actually just going to, rather than show you how it works, I'm going to show you the results. Here's the wedge being indented. It's a symmetric problem again. So here's half the wedge. This is just a cartoon to say, as I push this wedge into the soil, the free surface changes. And what's being shown over here is something that looks very dull, but in fact is really quite exciting. And that's that I can represent the surface using these bases that come from POD. So the way to explain this would be, to first approximation, you run the finite element calculations, you look at all of how the surface evolves, and POD tells you that to first approximation, that is what the surface looks like. You have to scale it for your particular problem, but that's what the surface looks like all the time throughout these problems. And there's no surprise there. This is the point of intersection with the wedge, and then there's a gradually decreasing profile here away from the wedge. And the concept is that POD tells you if you want to go further than that, if you want a better approximation, then you scale and add the next basis, which is this one. So if you want to refine this a little bit more, you add on this piece. And this, again, is determined completely by the data that you've gathered already for this problem. And by the way, it's sort of upside down. It's counterintuitive because you just multiply by -1 and you can flip it the other way. So POD doesn't care. And that is the second order approximation. You have to add that on to this one if you want to do a little better in representing the free surface. So now let me just show you how this works with it. And I'm sorry, these are kind of busy plots, but here's the force displacement relationship. As you push it in further, it gets harder and harder to push it in. Here's different wedge angles. It's from sharper to blunter. And lo and behold, the finite element calculations as the curves here agree pretty well. And you would hope, if you're building a data-driven approach, that you get good agreement. So this isn't fundamentally a surprise that you get good agreement, but sure enough, this approach, this surrogate model, does very, very well. You can build an architecture that gives you these force displacement histories. It starts to get a little more interesting. I was encouraging Ching Hao, push this until you break it. So here's the cylinder problem. And again, here's the first order approximation of what that looks like. And this one, you do have to flip in your mind. You have to flip this the other way around. It's upside down. And that's a pretty good approximation, but now you actually do have to add in the second order approximation to get a reasonable approximation of the free surface in total. Here's a plot that is sort of indecipherable, but the fact that the blue and the red are on top of each other, it's saying that as I push the cylinder in deeper and deeper, the blue free surface and the red free surface from the data-driven method are very close to each other. You get the free surfaces evolving essentially the same way in both methods. And here's where it sort of starts to break a little bit. You see that if I apply this whole approach and I'm looking at the force displacement history, well, now there's the FEM results, and those are actually the wiggly ones. I've forgotten that about these results, but those are a little bit wiggly. And as you look at the dots, which is the data-driven method, you get a smooth approximation to those curves. So, maybe it isn't breaking. It's actually even better. There's been some filtering in the data-driven approach, essentially. But you can see that there's some discrepancy that's starting, which you would expect. The last one that I'll show very, very quickly is the cutting problem. This is no longer sand. This is essentially clay, modeled as using the von Mises material model, perfect plasticity, fixed yield surface von Mises, or Tresca, if you like. And anyway, this is now the cutting problem. It's a plate moving from left to right, and there's this region of accreted material, which looks different now because it's a clay. It's a sticky material, essentially. And you can see here the first order approximation from POD. You have to flip it upside down in your own mind, but that's a good approximation. This is just a cartoon, but that's a reasonable approximation to what the lip looks like. And then if you want to do better, you have to add on this extra part, scale and add this, and that's refining. You can see really what the deformation looks like at the point of intersection with the free surface, which is, I think, a fascinating dimension of this that's vitally, vitally important. You saw that how these problems work is there's a concentrated zone of deformation which intersects with the surface, and this really has a huge influence in determining where that band is and how the force is going to change. I hope that makes sense. Forgive me if it doesn't. I'm throwing lots of information at you. And this is the end of the orthogonal cutting, and these are very busy, but still, I hope I can navigate you through them. Over here is the evolution of the surface. So this is just plotting the evolution of the surface ahead of the cutting problem. It's a plate being pushed. You have more and more material getting pushed up. So here's early in the process, and then as you push further and scale, because it's normalized, then you've pushed up more material. And what's interesting in this is we can go back and we can say, what if we had done a piecewise approximation? We just had a guess for what the free surface looks like. We hadn't done all of that POD business that I was just talking about. Well, it turns out I can't really get a very good approximation of the free surface if I try that. I need to have a better approximation of the free surface for it to work. And if I look at the forces versus the displacements from each of these approaches, the one that is based on the piecewise linear approximation of the free surface, this green line over here, it doesn't do very well at all. In fact, it has the wrong concavity in this plot. It's increasing at an increasing rate versus increasing at a decreasing rate is what it should be. So it's an interesting, what is interesting about this is these evolutionary plasticity problems are really tricky, and you need to know where the surface is at any given moment. And the point of all of this is to say that this proper orthogonal decomposition approach, if you have data, which could in principle be from experiments or simulations, you can do very, very well with that. Okay, so I'm done. I think that's kind of key outcomes from the National Science Foundation project, and a whistle-stop tour and incomplete at that. And I'll end by talking about what's happening now here at Cambridge, and with some concluding remarks about what we can make out of the story that is unfolding today. Coming to Cambridge, a very happy, I wouldn't say coincidence, maybe providence, was that we already had Cambridge in the civil engineering building. This is in our new civil engineering building where I'm talking to you from. We have two large 6-axis robots. They were here before I got here, and one of them turned out that its job was done with what it was envisioned for, and it was just sitting there as a piece of equipment that anybody could use. So no purchase of a 6-axis robot required. We learned our lessons with the fluidized bed, that even though it's a nice piece of kit, people are afraid to touch it and afraid to break it. It's an expensive piece of kit. So in this case, we've gone to using a expendable box. We can, if we drive the robot into the box, it doesn't matter. There's no fluidization now, so we have to be very, very careful if we're going to start thinking in detail about what the sand is and how we expect it to behave. But Joe Ingham, who I believe is listening, he took on this challenge. And the fascinating thing with Joe is that he's not a civil engineer; he's an electronics engineer, electrical engineer, and he's interested in robotics. So he's really interested in this end of the problem. And we're drawing him more deeply into the geomechanics end of the problem and saying there's a lot of work to be done here. So I'm going to show him some of his preliminary results. He got this setup up and running and has the robot able to do trajectories however we want. And we'll start with a very, very simple case, which is straight line motion. It's just moving the end effector straight through the soil. We have a sphere in this case because it's agnostic with respect to direction to the extent that any object could be. And he's just dragging this pushing it in and then dragging it across the soil. And you can see some parallels with what I already showed. Is this is now the evolution of the lateral forces. In green, Fy is the force in the direction of travel, and Fx is the one lateral force that's perpendicular to that. So you don't expect that to be a major player, but the Fy changes quite a bit as you push it into the soil. And then as you start to move from left to right, you have the evolution that's happening, and then something that's resembling the steady state. But it never actually reaches steady state in this case because the free surface wasn't level to begin with. So you can see the price we're paying for not having a fluidized bed is you have to level out the surface every time. We have no idea where the surface is in general when we start this problem. You can go in and do your best to level out, but this natural variation primarily comes from the variation of the free surface, which you would have in any of these sorts of problems. And this is really the demonstrator to say whatever elaborate type of motion you would have from your robot, you can program that in. Joe has made that work. This is a spiral that it's doing now. And what's interesting about the same Fx and Fy, as I described, the lateral forces perpendicular to each other. And as you're undergoing the spiral and moving outward, I believe, Joe will correct me if I'm wrong on that, then you actually have that you never reach a steady state because you're changing the terrain profile as you go. So automatically, these are really, really interesting problems, and interesting problems requiring some predictive methods for everything. And I'll seize this moment. I'm winding up now, and I'll seize this moment to say a few more general statements. And one is, in the course of doing all of this, I noticed actually, I spent a bit of time thinking about what is the definition of terramechanics, usually without the hyphen. And in my graduate class, where we started talking about these problems in seriousness and looked at the range of possible problems, we came up with this definition of they're problems that involve interaction between moving parts and terrain. And they're out there in abundance. So this list of problems where this is interesting has just grown since, at least since I started cataloging in my own mind and elsewhere, all of the problems that are here. You can read a little bit about this in some of these papers, and again, watch this, this video that I mentioned. And one thing that Joe and I bravely did was we decided that the latest incarnation of the problem, the one that he's interested in, is really the robotics problem. Robots interacting with soil to do all of these different things, earth manipulations, mobility, agricultural problems, you name it. We decided to start calling that subset of problems terra-robotics problems. I don't know that we need another term, but we're saying that this means interaction between robots specifically in terrain. You can read more about this elsewhere, and I won't say more. And that's where I'm ending with my general sentiments. Is now in this whole from structural engineering to geomechanics to soil machine interaction back to terramechanics, which has been a term that's been around for a long time, and sort of settling into terramechanics as the mother of all of these. In the Venn diagram, it's the largest of circles. And terra-robotics is the specific problem of all of the reasons why we would want to program things to do all of these different tasks. There's a lot of the applications, I hope, are relatively clear at this point, and there's a lot of problems that need to be solved. I've been emphasizing the fact that we really need models to predict what's going to happen, and those are extraordinarily lacking. We can run high-fidelity simulations, so-called high-fidelity simulations, but at the very least, they take a really, really long time. We're getting much better at that, but they still take a long time. They're very computationally onerous. If nothing else, they require a lot of energy rather than equations, which we can get results very quickly. We, as I showed, encountered the problem that we at this stage need to be able to map the terrain in real time. If you're ever going to get to automated earthworking and seeing where the surface is, we have to have some way of seeing where the surface is. We're working on that at the moment, open to suggestions. We have our own approaches and ideas, but mapping is an interesting problem. The control problem, if we're thinking about you have a task, you want to change the earth in a particular way, or you have a mobility problem, for example, where you have your own thing that you're optimizing. Working out how the control works there is something that this audience, I think, is very well accustomed to as an interesting challenge, and I don't have to convince anybody here of that. The idea that end effectors change dramatically depending on what you're interested in. You saw things that were bulldozers essentially here, but it wouldn't have to be. You could have, in mobility, you often have more penetration type processes, so there's a wide range of possible outcomes that you want, and topology optimization, changing the shape of the end effector, is going to be really important. And the last one that I'm very keen on as well is inverse analysis, because we need to agree on the fundamental soil parameters. That's a known issue in terramechanics. It's a known issue in geomechanics, and there's some interesting opportunities there in doing some mathematics on invertibility and then running experiments and seeing what we can get. So I'm at the end. I hope I haven't taken too much time with all of this, and I mentioned to Alex that I expected I was going to need some time to get through all of this, but I'm at the end, and I'll take a breath and suggest that there are some conclusions that can be made from this tale. And one of them, which is geared towards people who are thinking about who they are and what they want to do, and when you're in whatever position you're thinking about writing a grant proposal for whatever purpose or whatever is motivating you to do that, make sure that whatever you're thinking about is something that you're really interested in. This terramechanics subdomain is really of interest to me, and I can spend lots of years of my life doing it. So make sure you follow your interest and be yourself in the process. I put avoid distractions because there's always a lot of pressures that say, do something else. Get the easy win. Everybody's interested. We haven't applied for any money to do machine learning, for example. That this project, we were actually thinking about doing other things, but we just changed directions because Ching Hao happened to be very interested in that. So, but there's pressure always to adapt yourself to whatever is trendy at the moment, and that can be a distraction. There's also a potential issue here that you just get involved in too many projects. So I think I suggested this at the opening when I said I got interested in lots of things, and I realized at some point I really need to scale back on the range of problems that I want to do, and I want to do things that hang together nicely. Something that is really key here is convince yourself that your research is worthwhile. I mentioned in order to even have confidence proposing what I wanted to do, I had to go chase some numbers and think this is a big problem. So convince yourself that it's worth doing, and then you can use the ammunition that you've built up to try to convince others. There's a danger in there that you manage to convince yourself, and then for the rest of your life, you're convinced that this is always worth doing. And I think there's a trap there, but it is actually really key to go to that first step to convince yourself that it's worth doing. Otherwise, you'll never be able to convince somebody else that it's worth doing. And of course, this trajectory of moving around the world is not one I expected. And there was an openness to seizing whatever moment was there. So make sure you open yourself up as to the extent that you can to all available opportunities. All right, so that's sort of non-technical and more towards the aspirational part of all of this, and geared towards one subset of people who may have listened to this. The other thing is, in terramechanics, technically, it turns out, I hope I've convinced you today, that relatively simple principles can often give you very good results, and they're fast. So if you think about control problems and optimization problems for robotics, doing some of the things that humans or human-driven machines do at the moment very well, if we can get them to be quick, that comes with a lot of advantages. And there's lots of opportunities there. And those who've spent a lot of time in terramechanics know this from semi-empirical approaches that go way, way back. And finally, I hope that I've convinced people that this is just an open landscape, green field, terra-robotics. There's lots of applications. There's lots of fundamental problems. There is no need to be protective of an area. There's just so much for there are so many things for so many of us to do. And I hope that this has provided some ammunition to suggest that. And I'll end not by going through this complete list, but the key one here. There have been funders who've helped and organizations that have helped along the way. I think I've touched on these, but people who worked very hard on these throughout, it wasn't just me working on these problems, and I'm extraordinarily grateful to them. So I'll leave it on this slide, and I'll hand it over to you, Alex. Thank you.
Well, thank you, Jim, and particularly for taking us through the absolutely fascinating timeline, which has taken us from you as starting from an undergraduate to a graduate student, carrying out research, developing your interest in, and reaching the point where we are, or where you are now. And it's a common thing I think we often find from what you've been describing the last few minutes is the more we know, the more we need to know, or the more we don't know, if you like. And there is always more to find out. And the more we delve into things, and the more questions we tend to ask ourselves. And there is plenty of work still to do. I've got one or two questions. And before I come up with those, can I just ask anyone in the audience who would like to ask Jim any questions, could you please put them into the chat? And if you could write them out. If you wish to come onto the platform and talk to Jim in person, then we can switch you in so that you can join the platform and give your question verbally. But please ask a few questions. I'll kick off with one or two, but clearly we've got two general strands. One is developing a career from being an undergraduate through to obviously a very influential position in our terramechanics world and carrying out research and teaching. And also the technical aspect of some of the work that Jim has done. I can see from some of the names in the audience that there's going to be a few questions possibly coming, Jim, about some of the data you presented, which may open up a few avenues of discussion. So if you could add questions, please, if you could write them in the chat, and then I can see them and read them, and we will then bring those to the platform. One thing I picked up, I don't know if this is a starter, is I was quite interested when you were in Australia and you were doing the sand experiments. one of the things that came back to me, and it's often come back to me when carrying out any research work, is the importance of experimental observation and inquisitiveness. In other words, you start to see something and you ask yourself questions, then you may even do some little pilot tests, maybe fairly crude, and even from sort of walking over different materials and seeing how they respond to doing some simple blade experiments, and as you did with the Australian sand. Something which I often feel it tends to get ignored, the importance of experimental observation, but then being driven by inquisitiveness to find out, why is it doing that? Why is that happening? I don't know if you could, and it seems to me this is one of the things that through most of the work you've described, that's been quite an important aspect of how you've actually proceeded. I don't know if you've got any comments on experimental observation and general inquisitiveness.
Oh, too many, I'm sure, Alex, and I hope I don't bore anybody with this, but I completely agree with your idea that you need to be inquisitive, and curiosity, I think, is a key to being a researcher. It makes researchers who they are. So you have to indulge your curiosities. I'm actually a bit worried even that in the push towards computation and data-driven approaches, that, you know, we see this, I've seen this at every institution I've been at, the allure of moving to these areas. AI is the logical extension of that. And big companies that suck up all of the talent, and that's what we're spending all of our time doing, is we're kind of in this danger spot as humans, that we don't have enough people doing what you said, touching, exploring, feeling their way through. And I think something that I know now, Alex, that you and I share, is that that's in our background, that we grew up in an environment where we did lots of our own experimentation. Whether we even understood it to be experimentation at the time, we were always doing that. So I think from an institutional standpoint, from an education perspective, we need to make sure that universities continue to have robust laboratories. They have experiences for students where they go in, they test samples, they have to literally get their hands dirty. And that's not for everybody, but it's an essential part of engineering. And I could say a lot more about that. I've thought about, you know, ways that we can try to do that, ways within civil engineering that we can do that way. And I'm imagining ways within terramechanics specifically that you could really try to be more appealing to people early in their careers. And if there's interest in that, I can talk a bit more about what's in my mind. The other dimension of the answer to your question, I think, is that there's a lot of expectation around robotics. I started thinking about looking at construction robotics, and that's a landscape where the hype is everywhere, but there's not really that much necessarily happening. And when you think about these problems, you realize that human beings have earned what we've been capable of doing through physicality and through, using our hands, using our bodies. It's not all mental. It's a lot of the way that we experience the world is through physicality with the world. And embodied intelligence is something that's discussed a lot. So I think there's a lot that we have yet to learn about just how good we really are at interacting with the physical world. And that's really important to remember, that for the foreseeable future, robots are going to just be terrible at everything that they do. They're very good at predictable things, and they're just incapable of innovating, of improvising on the spot. And so if it's repeatable, if it's monotonous, that's the business of a robot at the moment. But any instance of any variability, and it gets stuck. And in automated earth moving and many other terramechanics problems, that would be key, to be able to improvise. So I think the importance of touching the soil it's for education as well as the research. And until we really wrestle with that in all seriousness, we're going to be stuck, even when it comes to developing robotics.
Well, thank you. We've got a question in from Devin Chen, if I pronounced that correct. And Devin has asked, as a current undergraduate with many varied interests, what suggestions do you have for narrowing focus areas particularly as I'm looking at a direct PhD after undergraduate, and I'm looking at potential candidates for PhD.
Mm. And I would welcome any other thoughts from others. That's such a good question. And it's such a, I mean, I'll answer in the obvious way, which is that there is a leap of faith involved. And I mean, I told you my tale, and there were many moments where I felt like I was taking a leap of faith. One of them was working with Professor Andrew Drescher, who I can only hope sees this at some stage. I can't imagine that he's seen it via the usual channels that these talks get advertised. But I had some reservations about, should I be working on this bizarre Department of Transportation project where wheels rolling across soils? And I got to know Andrew a little bit, and I thought this is an astonishingly interesting man, and there's so much to learn from him. And the project sounds pretty cool. It has lots of challenges. It sounds difficult, but in a sense, it was just that leap of faith that, yeah, I think I'm not done with education. I'm very interested in an advanced degree. I'm interested in doing research, and this sounds cool. And it was offered to me as an opportunity. I had known Andrew. I'd had him as a professor in an undergraduate class, so we had a bit of a rapport, and he came to me with this possibility. And that was one leap of faith. The other leap of faith was going to Australia. I thought, I don't know what I'm getting into. I don't even know if I want to be an academic, which is an interesting, conversation that we can be having. As I wasn't really convinced that this was going to be the right career choice. And Andrew was very encouraging of that. And I thought, okay, well, at least I'll do a postdoc. That's what it was in Australia to begin with. And again, I knew that there was going to be more problems. That was a little more open-ended. There was a set of problems that were there, and computational plasticity, different problems. And I thought, well, it plays to my strengths, but they're different problems. They're going to be interesting to explore. And I just took the leap of faith to do that. So I think you do have to just jump in and, what suggestions? Look for the opportunities. Maybe like I would suggest, what I'm thinking about is it's almost more important to find an advisor that you gel with than it is to really worry too much about the technical details of the problem. And Varsha's giving a thumbs up. I'm glad she has her own tales, I'm sure, in this respect. And just seize the moment. If there's something that looks reasonably interesting, get in touch with whoever it is. Look at what's out there. And then if you find yourself in the position that you're kind of inventing, I mean, that is a possibility. This is very US centric what I'm about to say, but there's the graduate research fellowships, and you can write your own proposal to do your own graduate work. And there it would be really key to follow to the first 3 pieces of advice that are up there, is that you want to make sure that you're really into the problem. You're excited about the problem, and then do a bit of work to make sure that you can get somebody else excited about the problem.
It also sounds a little bit as after you finished from your talk, after you'd finished your formal PhD, you were then in a position to actually widen your interests in the directions that you wanted to go rather more. So I don't know if that suggests is concentrate on getting the PhD where you've got support and people are interested in supporting you, and then possibly a little bit later you're going to be in a position to widen your interests a little bit more than while you're I suspect starting a PhD and then being drawn in too many different directions is probably not a good strategy from a student's point of view.
Mm-hmm. Agreed.
But we have another question. I think this one's a little bit more technical, referencing some of your data. This is from Cesar, if I pronounce it correctly, Arivalo, I think. In your closing remarks, you mentioned generalized soil response modeling. Could you elaborate on what this entails? Are you referring to a deeper refinement of the traditional pressure sinkage and shear stress displacement approaches, or do you envisage or do you envision extending or replacing those frameworks with new, more comprehensive formulations?
Thank you for your question. Such a good question. The way that when I made this statement, generalized soil deformation modeling, I was imagining the tools that are adaptable enough that you can adapt to different tool shapes, different ground engaging equipment moving in different ways. I think those models really are missing in many levels. So generalized, yeah, I'm being almost kind of deliberately vague in that, because there's many problems, many geometries that you can imagine, and there's many possible motions, and there's many possible soil types. So that's one of the things that leads to traditional pressure sinkage and shear stress displacement approaches, is that if you move to the semi-empirical models, that there's just a wide range of different responses within geotechnics, within soil mechanics. We know of all of the many variables that have created literally thousands of constitutive models for soils that include all of these different things. So that one statement has a lot packed into it, and I'm interested in efficiency. I mean, I don't know that I emphasized. I probably did emphasize this. In the past, I'm not sure I've emphasized this well enough. But we can build. I showed that at the very beginning, and others have done this. Many. And actually, I should give credit to Sally Shoup, Dr. Sally Shoup, who Varsha and I were talking about people reading papers. And when I was a PhD student, I was reading her papers on the finite element modeling of wheels. And then, there's a proud tradition of that in terramechanics going even further back. Those models those 3D finite element models are completely general, but they're very time intensive. So when I say generalized, I'm imagining analytical tools, analytical models that can try to approximate these responses. And then you mentioned deeper refinement of the traditional pressure sinkage and shear stress displacement approaches. When I started in this business, and I was reading Becker's books, I spent a lot of time trying to wrap my head around what are these Becker models? What are these tests and how do they work? And going again, even further back from Becker. And I think it'd be fair to say that when I started, I was quite skeptical of them. And now I think I've reached a stage of maturity in my life where I think these are great. You have to do what you can to get data and information. And that approach, those semi-empirical approaches, they just cut right to the chase of what matters in terramechanics problems and in mobility problems. And you see a wide range of parameters that you need to cover all of the possible behaviors. And I think it's a really great question that you asked, because there's clearly a mapping between those models and the rigorous, expensive finite element models with elaborate constitutive models that I was just talking about. And I think actually if you could make that link, then you unlock a lot of possibilities, and especially with respect to understanding how this works. I mean, I won't go on and on about it. The only thing that occurs to me to say is that I think data, I mentioned skepticism, but I'm kind of thinking now data in whatever form you're able to collect it is good. Because in the same thing, we have lots of, there's empirical approaches that are just based on penetrometer data, essentially. And that's better than nothing. If you have some piece of information, that's far better than knowing nothing. And I think to Alex's point about touching soils, the penetrometer is brilliant. You know immediately if it's soft or if it's very, very competent material. You have even an intuitive understanding of that, and presumably a robot would as well. So I think actually that back to that whole control of some of these other points is if you could make that link and you could go more deeply into these traditional models, you would actually unlock a lot of data that's already there that people could do interesting things with, and there'd be a lot of meaning and new knowledge that would come from that process.
Okay, thank you. I think there's several people in the audience who would very much agree with the comments you've just made there, Jim, and we could probably carry on with another discussion for quite some time around that. But if we can move on to, there's a question here from Peter Simon, and I think there may be other people in the audience who are thinking along a similar lines, and that is, what are your active projects at Cambridge? Are you looking for any European collaboration partners?
Yeah, great questions, practical questions. So active projects. I'm just getting my roots grown in Cambridge. I mentioned Joe, who's here, and Joe has taken on this challenge. I mentioned he comes from an electrical background, from an electronics background, and he's taken on the challenge of the automated earth moving problem. And what we're trying to do in that project is the map that we've had in our mind for where we're trying to get to is you have a box of sand or some other soil. It's sitting in some configuration at the moment, and you'd like a new configuration. You'd like to have probably one end effector on the end of the robot, whatever that might look like. Push a button and it will reach your target trajectory. Now, that is way harder than it sounds. And well, then maybe some people are going to say, "Oh, it's even harder than you're making it out to be, Jim." But for example, in our mind, you're not allowed to scoop it and move it out of the way. You're forced to deal with the fact that it's sand that's going to flow and have these slope stability problems that we were seeing to some extent today. And so, it's a complicated problem. You put an end effector on the robot, you move it some direction, and you've affected a change in the soil, but you're not really sure entirely what you've done. We have some ability to predict that, but some of it's going to be, the materials moving around in fairly unpredictable ways as we start this. And so real-time sensing of that is going to be really problem. And then building some kind of control problem that can handle that mess is something that's a challenge that Joe has taken on. And we have support for that project. And we're imagining that's multiple projects actually, and we're not going to get there by the end of Joe's time doing a PhD. And then we have another project that's more in line with, which is more in line with the sensing aspect of it, and what sorts of using the data that we're able to get, the 6-axis load cell on the end, to do inference of what the terrain is. So that's something that's coming in collaboration with people here, and that's something we will actually be advertising for that soon. So maybe I can seize the moment. Varsha did that great advertising at the beginning, and it's not official exactly yet, but soon we'll be putting out an announcement for a postdoctoral fellow who will come and help us in the lab with the kind of a lot of these different problems. And I'm imagining that person would be sort of a jack of all trades, interested in quite, any of these things and all of these things, if you like, that are on the screen here. I think and we're always interested in more. So I have a few industry partners that I'm talking to again. I mentioned Caterpillar it was great to be with them in Illinois. That we now have the tyranny of distance between us, but the virtual product development group that does simulation is very interested in the model building, or was, and I would assume still is. I'm interested in pushing those along. Anyway, I could keep going, but the second question is, are we looking for European collaboration partners? Yes, yes. And I'm going to make the statement that I am not a roboticist. That's actually what Joe and I have forged this collaboration, and he's very interested in this subject. And I come from the soil mechanics, the civil background, and so on. But I'm imagining that there are roboticists out there that have already done a lot of things in control, and maybe even thought about these problems. In fact, I would say, I don't know if anyone is listening there, but there's a group at ETH Zurich that we've been looking at. They've been moving in this direction. I need to learn. It's always a learning problem. So absolutely, I'd love to get in touch with anybody who has similar interests.
Right, thank you. Just a slight follow on for that one a little bit, Jim, and that was one thing that we did briefly discuss before, and just see what your thoughts are. How much did you find that the academic environments in the US, Australia, and the UK, how much difference have you found, and how difficult was it to adapt? I suspect you may find that Cambridge is slightly unique possibly for the UK, but there may be a UK feeling that you found compared to Australia and the US.
Yeah, thanks, Alex. so the US, I've seen it multiple ways, both as a student and then as a faculty member, and I think that's worth reflecting on a little bit. The US continues to be a good place to do science. It's going through some tough times at the moment. There's no secret about that, and the funding that used to be available to probe all of these different problems and explore. I mean, I think the research funding at its best, it's the fuel, it's the enabler that lets people indulge their curiosities, to Alex's point earlier. And I mean, if research organizations, peak funding bodies funded through the government don't pay for that, I mean, who does pay for that? Because companies, usually are only interested in something that has commercial potential, and they're not very interested in something that doesn't have a good technological readiness level yet. And, admittedly, you look at the things that I presented, it's, well, this is a very low level of technological readiness that we're talking about. It's the fundamental things that underpin that and lead into all of that. So, I mean, the US continues to be a really, really vibrant place. There's just so many, I think even to this day, it's changing very quickly, but you'll find there's lots of players and lots of appetites to do fundamental and applied things, and there's different agencies. Nowadays the federal agencies are struggling, but there's state agencies. I mentioned this first project, which is a Department of Transportation project. So within each individual state, you will find that there's some very interesting work going on, and that's actually what makes it so wonderful. Is each of the 50 states has kind of often a completely different ethos, completely different set of opportunities. And I think that would be that comes with the challenge. You need to find those opportunities. You have to put yourself out there. You have to do a lot of work sometimes to figure out where people are and go to conferences. Alex and I were talking about this the other day, the importance of, and this speaks to the last point of open yourself to all available possibilities. Everybody here needs to go to the next ISTVS conference. That's the whole point of going to conferences, right? Is meet people, make unexpected connections. So the US, is an interesting one because it's changing so quickly. The Australia was, when I went there, it was extraordinarily favorable to infrastructure. That project that I mentioned, at the very opening, I mentioned Professor Scott Sloan, that he was successful in building up this center, and there was a willingness to look at infrastructure, and it was offshore problems and it was onshore problems, including railways, and there was a real willingness to invest. I would imagine that has moved around since the time that I was in there, and I don't know what it looks like exactly now. One of the disadvantages of Australia is that the academic scene, and I think maybe that's a little closer to England, I'm not entirely sure, is that faculty positions get to be a little grayer, and there's a move towards more of the positions where are soft money positions that you pay for them out of research grants, and I think universities are threatened by that in a way, and there's lots of pressures that have led to that. But Australia, I felt it there for the first time, that there's a high quality of life and people are generally happy. Academics at universities are under a lot of pressure. And it's a kind of strange pressure that you feel like, you need to go earn some money in order so I think that this is the practical, useful dimension of what I've said here is, I understood it was going to be very good to start thinking about funding, because that enabled lots of things. And some people even just pay for their own. I wasn't in that position, but pay for their own salaries out of money that they've won. So I think that's a little difficult. And Australia seems like it was sort of ahead in that, in a way, is that the US, there's pressures been building in the US to move teaching online, do away with brick and mortars, and it's created real difficulties in the university, which, by the way, this is a separate talk entirely but I intend to use my own position to try to make sure that universities keep doing what they're meant to be doing very well, which gives young people an experience to be there in person, to interact in laboratories with smart and capable people, to figure out who they are, and we certainly don't want to go too far in that virtual direction. We want them to be lively places where people have time and bandwidth and the ability to think, and they don't have the time pressures to think. Moving back to the US, I think then that was where I saw that US universities were kind of, for various reasons, they were moving in that direction. They were becoming more tense places, it felt like, for faculty in various respects. And in that sense, I guess that comes to England, Alex. And you mentioned Cambridge is a special place, and I think it will always be a special place. I found it to be very refreshingly bottom up, that the faculty are still in charge here. So if I'm sounding like I'm empowered, that's what I want to try to help US institutions and Australia institutions find their footing on that again. And the UK in general, I think it's been less obvious to me to find a place for me in the funding calls. I'm in a position, admittedly, where I'm given a lot of freedom, and I should be doing good work. Do good work. Whatever it is you're doing, do good work and put the emphasis there. And I would encourage anybody at any level thinking about this is that really should be everybody's mantra, is just do good work. But coming to England and coming to Europe, it has been more challenging than it was in the US and Australia to see where my interests fit with what is being funded by various bodies. And I haven't done the job that I should be doing, probably looking closely, chasing. And actually, I don't want to go on too long about this, but I think one thing that we all have to do is we have to make sure that our voices are heard in getting people to put out the right calls. There's lots of mechanisms for feedback there. And the best way to try to get some funding going in the area that you're interested in is to reach out to the people who are putting out those calls and make sure that it's on their agenda. And so Peter Simon's question about, are you looking for European collaboration partners? Absolutely. And we need to form our consortium of terramechanics-minded people who are lobbying for resources to do some of this work.
Yeah, thanks, Jim, for that. I'm sort of looking through your conclusions at the end there. As an agricultural engineer, then obviously the one that comes to mind there was the looking for new smart machines, particularly agricultural machines, and some of my interest areas around precision tillage or minimum precision tillage using very precise operations around plants and so on and weeding. And it seems to me that in the world of terra-robotics, there is plenty of scope for work to develop on there. But that's from my direction a little bit, being a little bit more problem orientated towards solving problems in the field. But overall, thank you. That was absolutely fascinating timeline of taking yourself through and developing your ideas and developing your understanding, and also asking new questions as your understanding develops. So I think it remains for me just to say thank you very much for an absolutely fascinating talk. And if you don't mind me just paraphrasing the BBC science reporter, Jim Al-Khalili, thank you for taking us through your early life scientific, and I hope that you've got many, many years left to continue on this work. So thank you very much indeed for the talk and the presentation.
Well,
and
thank
if I
you,
could
Alex.
just,
thank you.
Thank you very much.